Center, along with me, Mark Anderson, and another researcher who's the head of the Diabetes Center at UCSF, Matthias Heybruck. And I'll mention at the outset that one of the points of this little story is to highlight the importance of collaborative research. In this case, it was two investigators who had never worked together, working together for the first time and coming up with something that's absolutely groundbreaking. And you'll see over the next set of 5 to 10 years that collaborative research, more and more involving researchers around the globe working together, being enabled by social networking, being enabled by computer-generated cloud-based databases, being enabled by video chat, and mechanisms like this that have nothing to do themselves with diabetes per se will enable people to work together to do things that they could never do just by working with people in their own institution. But in this case, two people who'd never worked together at UCSF worked together. Mark Anderson's group works on a gland that lives in the neck called the thymus. The thymus is an educational center. It is an organ that teaches our body's T cells, a linchpin of our immune system, to recognize what is a foreign invader that should never be in our body versus what is a part of us that we should not attack. And as most of you may know, type 1 diabetes is a disease where that system goes awry, and T cells, among other immune cells, actually attack your own pancreas. So the fundamental defect in type 1 diabetes is not one of the pancreas. It's not one of insulin. It's a fundamental defect in our ability to recognize self from non-self. Okay? And so what Mark Anderson's group has done is to try to understand how you could use stem cell biology to generate thymic cells that will re-educate T cells to quit misrecognizing self for non-self. Okay? And Matthias Heybruck's lab has come up with a technique to use, again, stem cell biology to try to create a cell that is very much like a beta cell. So what they did is to use these two techniques in combination in a mouse model of diabetes, type 1 diabetes, okay? And they used stem cells, introduced them into this mouse, and were able to accomplish goal number 1, which other researchers have accomplished, and that is to get that mouse to make insulin. Okay, using stem cells. And I'll get to the point about why stem cells are so important in just a moment. And then, in combination with Mark's group, they also gave these mice a set of stem cells that were differentiated to become thymic cells, so that these cells that Matthias's group gave would not be misrecognized as non-self and attacked. And that strategy worked. So with this two stem cell model, the mouse was able to make insulin with stem cell derived beta cells, and the mouse was able to let those cells live and not attack them, overcoming the fundamental problem in type 1 diabetes. Now, of course, this is a short-lived result in mouse, which is a far cry from a long-lived result in human. But the approach is revolutionary and never has been taken before. And stem cell biology is allowing this to go forward, and collaborative research is what really was the kismet in this case, getting this to really result in a phenomenal result in this mouse model. So that's one set of experiments that came out this year. And the stem cell thing is important because pancreatic transplant, islet cell transplant from donors can, in some cases, work, but it requires lifelong anti-suppression medication to prevent you from rejecting what you were given. If you can take someone's own cells, coax them to become stem cells, and then teach those stem cells to become thymic cells and or beta cells, and give them back to that same person, you don't need any medicine to get over suppression, because you'd never need it, because you wouldn't attack them because they're from you. They're not from a donor. So this is really revolutionary stuff.